Okay, let's look at this past paper question. This past paper question is from Gauteng. It's the September 2019 Newton's Law preliminary trial exam question. It says a horizontal force FA of magnitude 20 newtons is applied to block X with a mass of 3 kilograms on a table. Block Y with a mass of 2 kilograms is resting on block X. The two blocks are joined by a thin, inextensible string of negligible mass which runs over a frictionless pulley fixed to the wall. Block X experiences a kinetic frictional force of 1.2 newtons with the surface of the table. There is no friction between block X and block Y. Okay, and the tension in the string is T, here's T, when block X accelerates to the right. So they're telling you this is the direction of acceleration, which means that the friction is going backwards. Okay, state Newton's second law of motion in words. Learn your definitions. This is the definition linking force and acceleration, that an object will only accelerate if there's a net force on it, and that acceleration is directly proportional to the force and inversely proportional to the mass of the object. Make sure you know it off by heart. Now it says to you, draw a labeled free body diagram showing all the forces acting on block X. Now this is block X, this block on the bottom. Remember, with a free body diagram, this is 6 marks, I need 6 arrows. So we can start off with all of the obvious things. Okay, so here's block X, which is 3 kilograms. Now remember, there's 2 blocks here. We're inevitably going to have to draw both free body diagrams for both blocks, but we'll start here. So you make your little blob in the middle and you get out your ruler, and the first thing we know is this block weighs 3 kilograms, so acting vertically downwards is the acceleration due to gravity, or the weight of the object, and that is Fg acting downwards. The object is on the surface of a table. The moment any object is on a surface, we have a normal force at 90 degrees. Remember now, the mark is for the arrow and the label, and they must all be coming out of the block. The next obvious force is there is an applied force coming out and to the right, and this is 20 newtons if you want to label it. The other obvious force is there's very clearly a string with a tension T coming out to the left. So those are the 4 most obvious forces. The block is accelerating to the right, and they told you there was kinetic friction. So there's a force to the left of Fk, and if you want to, you can put in the value of 1,2 over there. And then we are short 1 force. So what force are we missing? We'll have a look over here. Here is a great big 2 kilo block resting on the 3 kilo block. It will be pushing downwards, and so there will be a force here. This is also a weight force, but it is the weight of Y on X, because Y is pressing down on X and its force is going straight downwards. So there we go. There are my 6 arrows coming out of the diagram, all neatly labeled. Now it says calculate the magnitude of the tension T in the string. So obviously we're going to use Newton's second law, F net equals ma, to solve this. But we have 2 unknowns. We don't know the acceleration and we don't know the tension in the string. So simultaneous equation, here we come. Before we start, we need to draw the force diagram for block Y. Okay, here is block Y. Block Y, fairly obviously, has block Y's weight pressing downwards. Block Y is on a surface, which happens to be block X, so it has to have a normal force. But now they said to you there is no friction between block X and Y, so I can't draw in friction, but have a look here. Here is a string with a tension T coming out of this block, so I have a string with a tension T coming out there. And those, as far as I'm aware, are the only forces on block Y. So if we want to calculate the magnitude of tension T in the string, we must make a simultaneous equation. So let's start. F net equals ma. This is a 3 kilogram block, so ma is going to be 3a. What are our net forces? If we say the direction of motion is positive, then we can have a look and we can put these forces that are in a straight line. We can start adding them. So FA is positive because it's the direction of motion. FK is going backwards, so it's minus, and T is going backwards, so it is minus. When we add a plus and a minus, it becomes a minus. So that is the vector sum. We don't know. FA is 20, FK is in the question, it's 1.2 newtons, and we don't know T, and this is equal to 3A. So 20 minus 1,2 is 18,8 minus T equals 3A. So this is probably my equation 1. If we come to block Y, we can say again F net equals MA. What forces have we got here that are in the direction of motion? We literally only have T. T is the net force, which is equal to MA. The mass is 2. We don't know the acceleration. So what I would do here is, it's pretty easy to say that A equals T over 2, because this was my second equation. So if I say 2 into 1, sorry, excuse me. If I say 2 into 1, I can go 18,8 minus T equals 3 times T over 2, because we said A equals T over 2. So 18,8 equals, take the T over, T plus 1,5 T. So 2,5 T equals 18,8. So T is going to be something like, I think it was 7,52 newtons if you use your calculator. There we go. This part of the question is done. So then we go and have a look at the second part of the question. The second part of the question is a Newton's law of universal gravitation question. It says a learner wants to calculate the distance between the Earth, he has the mass of the Earth, and the Moon, he has the mass of the Moon, where the net gravitational force is 0. To achieve this, the learner's placed a third mass M, here's M, at point P, as shown in the diagram below. The distance between the centers of the Earth and the Moon is R. Okay, well, if we look at this diagram here, we've got this distance R between the Earth and the Moon. We've got this distance X between our little mass M and the Earth. And so this means this distance here, because we're going to need it, is going to be R subtract X. Okay, so those are the distances that we need. So state Newton's law of universal gravitation. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. Okay, it's an easy formula to, easy definition to learn. So we use this formula, F equals G M1 M2 over R squared, where that big G is the universal gravitational constant, M is the mass of the object, and the other M is the mass of the planet, and R is the distance between their centers. So let's have a look at what's going on here, first of all, before we go any further. If we have this object P here, what is happening to the object P with regards to the Earth? P wants to go this way. The Earth is trying to suck P towards it, okay, because that's how gravity works. You're going to be attracted to each other. But what is happening to P? The Moon is trying to suck P into it as well. And what they've said to you is the net gravitational force is 0. So that means that the Earth is trying to pull P into it, and the Moon is trying to pull P into it. Sorry, not P, it's M. It's at the point P. So when you put M at the point P, the Moon says, come to me, M, this way, and the Earth says, come to me, M, the other way. So if you know these are vectors, one of these is going to be positive, and one of them is going to be negative because they're in opposite directions, because this is how we know that there are vectors. Okay, so if we had to name these forces, this force on the left here, going to the left, is the force of the Earth on M, and this force going to the right is the force of the Moon on M. And it says to you the net force is 0. So when we find the net force, we add the forces together. So the force of the Earth on the Moon, on M, sorry, plus the force of the Moon on M is going to be equal to 0. But what we have to bear in mind is that this, when we add them together, if we say to the Earth is positive, okay, we end up with the force of the Earth on the Moon minus the force of the Moon on M is equal to 0. Sorry, I think I just misspoke there. There's too many M's in here. Okay, but you get the picture that the one force is positive, the one force is negative, because they're in opposite directions. So what this means is that the force of the Earth on M is going to be equal to the force of the Moon on M, because when you take it over, the one becomes positive. And now we're going to just substitute into this formula, okay, G M1 M2 over R squared. So G, if we're looking at the Earth on the Moon, G is a constant, it stays there. M is the mass, the one little mass, and then the mass of the Earth is given in the question. So this is multiplied by 5,97 times 10 to the 24. And then this is over the distance R squared. But what is the distance between the centers of the Earth and this object M? It is this X over here. So this is over X squared. And this is now going to be equal to the force of the Moon on M over here. So this force is also equal to G M1 M2 over R squared. So G is a constant. The mass of the object, little object, is M. Now we need the mass of the Moon, which is 7,35 times 7,35 times 10 to the 22. Lovely big numbers. Okay, now what is R squared? It's the distance between the little object M and the Moon, and we worked out right in the beginning that this is R minus X. But now this has to be R minus X all squared. So we in actual fact have to make that little quadratic equation. If you think about it, R minus X times R minus X, and by FOIL or whatever you want to call it, it's R squared minus 2RX plus X squared. Okay, so if we FOIL that, that's what we get. So now if we have a look at our equation here, what have we got here? We've got a G on the left and a G on the right, so I'm going to divide both sides through by G. They're going to disappear. I'm going to divide both sides through by M. The M is going to disappear. And now I am going to cross multiply across the equal sign. So I end up with 7,35 times 10 to the 22 X squared is going to be equal to 5,97 times 10 to the 24 times whatever this expanded out to as R squared minus 2RX plus X squared. And then if you distribute this out and you work everything out, you end up with some complicated sum with big numbers. Okay, what you do here is you've got X squared on the right, so you bring it back over to the left to make this equal to 0, and you end up with all of these big numbers. Okay, big numbers, I don't want to write them, but you could work them all out on your calculator. And then what you do is you divide through. Can you see this equation here? Okay, this equation here has got the r squared has got a coefficient of 1. So whatever the coefficient of r squared ends up being, it's this 5.97 times 10 to the 24. You divide all of the big numbers through, you divide them through by the coefficient of r squared. Okay, and then you will end up, goodness me, that handwriting is shocking. Okay, you divide everything through by the coefficient of r squared, okay, and then you're going to end up with this equation, provided you've put all the numbers into your calculator correctly. But have a look here, don't agonize over this too much. This is 4 marks, so probably the 1 mark is for the formula, and then the other important mark is for this recognition here. You need to recognize here that one of these is positive and one of these is negative, and that when you find the net force, you add them together, and a plus and a minus make a minus. And then you've probably got this mark, and then this mark, and maybe this mark, and then all of this maths is incidental to getting you the last mark where you prove this. So the most important thing that they're checking here is actually that you understand what the vectors are doing.